Hello, everyone. My name is Jeong Kim. I am a postdoc scholar at Stanford University. My talk at the symposium is Parent Interference Radiation Force, PUF in short, neuromodulation with improved spatial resolution and focus control. So let's look at the background first. Transcranial focused ultrasound and PUF. Here we have three figures, and in the left, we have transcranial, conventional transcranial focused ultrasound. In conventional method, we have radiation force in the large area. And due to the attenuation in tissue, the radiation force is not strong. So we proposed PUF. In PUF, there are two transducers facing each other and generate standing waves. In standing waves, there are nodes and antinodes and very sharp pressure gradients, therefore strong acoustic radiation force. However, still we have the radiation force over the large area. So here what we are trying to achieve is to have confined radiation force in space, and also to be able to control the location of the focused radiation force in space using pulse compression method. And these are the pulse compression method I used in this work. I used CHOP, frequency stepping, which are frequency modulations, and barcode code, a kind of phase modulations. So CHOP, we increase frequency of the signal in time linearly. And frequency stepping is similar kind, but frequency is increased in stepwise. And in every step, the increment in frequency is fixed. And barcode code is the most efficient phase modulation method. And in this work, I used 13-bit barcode code. So let's look at the frequency modulations. Here I used 200 kilohertz to 1 megahertz CHOP and frequency stepping signals into those two transducers facing each other. And I conducted 2D pressure scan with a membrane hydrophone. And these are the pressure scan method when I used 15 cycle sine burst, CHOP, and frequency stepping. So when I used just multiple sine burst, I have very clear standing waves over the large area. But with CHOP and frequency stepping, we can see that the stronger pressures are centered in the middle. And when you see these areas, the pressure gradients are not strong. So when we calculate acoustic radiation force from this pressure field, we can see that with CHOP and frequency stepping, radiation forces are focused at the center, and the area is very confined. And in terms of distance, we have radiation force focused in about 2 to 2.2 millimeters, while using 15 cycle sine burst, we have radiation force over the about 30 millimeters in distance. And this is barcode code applied sine burst. So here I have 13 cycle sine bursts with barcode 13 code applied. So in this signal, we can see cycles with the phase shifted. And the same, I input this signal in the two transducers and conducted a 2D pressure scan. And here we have very clear standing waves when you used 13 cycle sine burst over the large area. And with Barker 13 applied sine burst, the stronger pressures are focused more in the middle. And we do not see much pressure gradient in these areas. So when we calculate acoustic radiation force, again, we see that acoustic radiation force is very confined in narrow region when you used Barker 13 applied sine burst. While using 13 cycle sine burst, we still have radiation force over the large area. So far, we have seen that radiation forces are focused at the center. And what else we can do is we can electronically control the focal spot of the radiation force electronically. So these are the pressure scans. The location of the focuses are controlled electronically. And when we calculate acoustic radiation force, we can see that acoustic radiation forces are focused very well in different locations. So acoustic radiation plus we've seen so far are the calculations from this pressure scan. And to be able to make sure that our calculations are correct, our team conducted direct measurement of acoustic radiation force using PDMS cantilever. So here, when you look at the configuration, we have two transducers facing each other to create standing waves. And we put a PDMS cantilever and we shed a laser light on it. And we recorded movement of the PDMS cantilever due to the acoustic radiation force. And we recorded the movement with an optic system. And by the way, this work is under review at Ultrasonics. And this slide compares the acoustic radiation force calculation and the direct measurement of the acoustic radiation force, particularly these plots. So here, the red plots are the direct measurement using the PDMS cantilever of the acoustic radiation force, and the blue, and the black curves are the calculated radiation force from continuous wave and from chop. So we see that those two red and black plots matches pretty well. And we can trust our calculations. So let me conclude. We presented pop with confined radiation force by size. For example, with 15 cycle sine burst, it was over the 30 millimeters of distance. But with the chop and frequency stepping, we could confine it in about 2.2 millimeters in distance. And we also showed the electronic control of the focused radiation force position. And we demonstrated the direct measurement of radiation force and showed that our radiation force calculation is reliable. And in the near future, we will conduct experiments in phantom and in vivo setup to be able to see how it works in more real situation. And thank you for your attention. Thank you so much.